This is a buck converter, which can deliver up to 3 amps. This is based on MP1584 ENIC, and I want to test it multiple ways and later on compare it to, I would say, the most popular LM2596. So let's go. Hello world and welcome. First, let's take a look at our buck converter. So you have your input side, you have your output side, you have your inductor, you have your diode, and you have your IC. Here you have your potentiometer. If you rotate it counterclockwise, then the output voltage will go down. If clockwise, then the output voltage will go up. The difference from the LM2596, the potentiometer is very small, so the tolerance is very tight. If you go more than 9 volts, it's very hard to get the precise voltage. On this one, yeah, you have much more precision with this potentiometer. And this lacks the capacitors on the input and on the output side. Now let's look how I tested all of this. The environment that I'm testing in is 24 degrees Celsius plus minus half degrees. The humidity is 25 plus minus 5. And all the tests that I've done on every run is for 30 minutes. Then the converter is cooled down, and then I run the next test. Everything's in open air, so it's without any box, it's without the heat sink or any additional airflow. I wanted to measure with my thermal camera 3 components, and I checked the stability, the voltage difference, the amp rating, and of course the efficiency. Now let's dig into the data. I'm running multiple tests, so from 5 volt to 3.3 volt, 12 to 3.3, 12 to 5, 24 to 12, 24 to 5. So I would say most common ones. IC max temperature is 125. The same goes for the diode and same for the inductor, which I checked from the datasheet. So from 5 volt to 3.3, everything's good. The efficiency is great. The voltage drop is minor and the temperature is pretty solid. From 12 volt to 3.3, same story. The efficiency great, the temperature is great, the voltage difference is minor. From 12 volt to 5 volt, the voltage little bit bumped up, and we'll see that later, like why I care about this. So the efficiency is great, the temperatures are great. And then we go to 24 volt to 12 volt. Before the load, I set the voltage exactly to 3.3, to 5 volts, and to 12 volts. So it bumped up to 13.1 volt. At this point, yeah, that's a no-go. So that means on the load, the output voltage can differ, which is strange. Like, this is a big margin of error. So consider that. The efficiency, yeah, it was not so good, but still workable. Temperature is good. From 24 to 5 volt, the voltage went up a little bit, but yeah, still like in more or less 2%. So it's like 2.7, 2.8. So we're still good. The efficiency is good. The temperature is good. So next up, 1 amp. So we lost 5 volt to 3.3 volt. I managed to squeeze out 0.6 amps on the output side, but then it started to crash. What I mean about that, the voltage dropped to 0 and rebooted, then to 0 and again. So we lost this fight. From 12 to 3.3, the voltage dropped, 3.21. Still workable, but not so much. The temperatures are good. From 12 volt to 5 volt, we lost 0.15 volts on the output side. Still workable. The efficiency is not great. The temperatures are good. 24 to 12 volts. Now we went below 12 volts, so it's now 11.88 volts. The efficiency is good. The temperature's still fine in this range. So 24 to 5 volts, like everything's good. The temperature is good. The voltage is good. Great. Now 1.5 amp. Here, now it looks a little bit more different. So from 12 volt to from 12 volt to 3.3 volts, we went to 3.15 volts, like to, I don't know, power some sensors or microcontrollers. It's not a good voltage. The temperatures were still fine. The efficiency, okay, good. 12 to 5 volts. We lost here. It's 4.45. So a lot of the hardware will not like this voltage. The efficiency is 72%, and we went on the IC 106 degrees, which is not good. Like in open air, okay, fine, but in the long run it will go up. So I would say this is a no-no. So 24 volt to 12 volts, we went to 11.72 volts on the output side. Still workable, but the temperature on the IC went to 118 volts. So this is a no-go. You can add a heatsink on it and add some airflow, then it would be fine, because it's only one component. The diode and the inductor are good. On the 24 volt to 5 volt, the voltage is good. The temperatures are rising. Still heatsink. The same goes for everything. Like it needs some cooling. The voltage, not so good. And 2 amp tests. Now this is a shit show. So 12 volts to 3.3 volt. 3.18 volts on the output side. It started to crash after 15 minutes. The temperature on IC went to 130 degrees Celsius. So this is a no-go. On 12 volt to 5 volts, I got it working on 1.55 amps max, so 0.05 amps more, and it started to drop below 4 volts, then to 0, and then reboot, and again. So this is not gonna happen. 24 volt to 12 volts. The voltage on the output went to 0.7, but that was only on 1.6 amps on the output side. On 2 amp, it crashed after 30 seconds. I didn't update it here, so it's only 12-minute test. So after 12 minutes, it crashed. So there's no option for this. On 24 volt to 5 volt, the voltage is good. On 2 amp output, it crashed after 67 seconds, and then I tested 1.7 amp output, and it went all the 30 minutes, but the temperature on IC was 122, so we're maxed out. So what's interesting to know is the diode and the inductor, they're good, so the IC is what's heating up. So at this point, definitely a heatsink would be needed. I will not try to add a heatsink because heatsinks are different, and for the airflow, what fan do you use, and the enclosures are different. Most of the people buy these as is and use them as is. I've tested the LM2596 only. The minimum volt amps, was 1 amp, and I'm going to show you the data only on 12 volt input and 5 volt output. So let's begin. 1 amp test, both look good on the temperatures and on the voltage difference. Yeah, the MP1584, the voltage dropped a little bit more than I wanted, but still workable. On 1.5 amp, like the LM2596 is the king. The temperatures are much lower and the voltage is much better. Then I go for 2 amps. As you've seen before, we can't pull from this 2 amps. It's 1.55 amp max, so I would say 1.5 amp maximum. 2 amp on the LM2596, it gets too hot, so actually like the maximum on it is 1.5 amp. And you would need a cooler for the MOSFET and the diode. So what's our conclusion? You can use this buck converter for, I would say, 1 amp, 1.5 amp. It definitely needs cooling, but the benefit is that it needs only cooling on the IC. The other thing that the size of these are day and night. So for small projects, this would be very good asset to use. I don't know the ripple on the output. I don't have the gear to test it, but so I would go for 1 amp on this if you need a small size, but the LM2596 would be better, even that it has the capacitors on the input and on the output side. So if you like this video, get subscribed, give me a like, write a comment like what you want me to test next, and so that's it for the video. Bye.